You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Data sanitization is the deliberate and structured process of ensuring that information is no longer retrievable from storage media or services once its useful life has ended. Unlike simple deletion, which may only remove a pointer or directory reference, sanitization aims to remove any possibility of reconstruction, even through forensic techniques. In traditional IT, this might involve wiping drives or physically destroying disks. In cloud environments, where physical hardware is abstracted from tenants, sanitization often relies on logical methods, encryption, and service-level controls. The importance of sanitization cannot be overstated. Without it, retired systems or recycled storage media could become sources of unintentional leaks. Secure deletion offers peace of mind that when data is no longer needed, or is legally required to be purged, it truly ceases to exist in any recoverable form. The National Institute of Standards and Technology, NIST, codifies sanitization practices in its special publication 800-88, a globally referenced guide for secure deletion. This standard defines how organizations should select sanitization methods, verification techniques, and assurance levels appropriate to different scenarios. For example, a laptop containing sensitive medical data may require different sanitization than a temporary log server. NIST SP 800-88 recognizes that technologies evolve, and its recommendations encompass not only overwriting techniques but also cryptographic and hardware-based methods. The document's enduring role is to provide a trusted baseline so that organizations can confidently demonstrate compliance and avoid guesswork. Citing SP 800-88 in policy signals both rigor and alignment with best practices, reinforcing that sanitization decisions are structured rather than improvised. NIST outlines three broad categories of sanitization: clear, purge, and destroy each, with distinct assurance levels and operational impact. Clearing involves overwriting or resetting logical addresses, sufficient for low-sensitivity scenarios, where only basic recovery tools need to be defeated. Purging applies more rigorous techniques, such as cryptographic erase or hardware commands, to protect against sophisticated forensic recovery. Destroying is the final and most drastic option, rendering media physically unusable through shredding, incineration, or degaussing. Each category corresponds to a business context. Clearing may suffice for lab test data, purging for production databases, and destruction for hardware leaving custody. Understanding these distinctions allows organizations to tailor sanitization strategies proportionally, ensuring neither under nor over-engineering of controls. Crypto erase provides a powerful alternative by destroying encryption keys rather than overwriting entire media. When data is encrypted, its confidentiality rests entirely on the secrecy of the key. By making that key irretrievably inaccessible, whether by deletion or revocation, the data instantly becomes unreadable. This approach is highly efficient, especially in cloud environments where large volumes of storage may be impractical to overwrite. Crypto erase is often invisible to users, occurring as part of automated retention or decommissioning workflows. The elegance of the method is that the encrypted bits remain untouched, but without the cryptographic key, they are meaningless noise. It is the digital equivalent of changing the locks on a vault so that even though the contents remain inside, they are permanently sealed away. Solid-state drives, or SSDs, complicate sanitization because of their underlying architecture. Unlike spinning disks, SSDs rely on wear leveling, remapping, and garbage collection algorithms that move data blocks unpredictably across the device. This means that software-level overwrites may not touch all areas, leaving fragments recoverable. While some SSDs implement secure erase commands at the hardware level, results vary across vendors and firmware. Consequently, cryptographic methods are generally preferred for SSD sanitization, since revoking encryption keys bypasses the need to track every block. The complexity of SSD behavior highlights why traditional overwriting approaches cannot simply be transplanted into modern contexts. Effective sanitization must respect the nuances of the medium itself, tailoring methods to how data is physically stored and managed. Hard disk drives, or HDDs, remain more straightforward to sanitize, though their characteristics introduce their own challenges. Because data is stored magnetically, overwriting can reliably obscure prior values, provided the operation is performed thoroughly and multiple passes are used for higher assurance. However, overwriting large-scale HDD arrays can be time-consuming, resource-intensive, and less reliable than cryptographic alternatives in distributed systems. Moreover, as drive densities increase, the precision of overwriting must keep pace to defeat advanced forensic recovery. While HDD overwriting still has its place, particularly for legacy systems or lower sensitivity scenarios, organizations increasingly rely on crypto-erase or hardware-supported commands to achieve faster and more scalable sanitization without exhaustive physical writes. Cloud storage abstracts away the underlying physical media, making traditional wiping impractical for tenants. Users cannot access the drives that host their objects or volumes, so sanitization shifts toward logical deletion and cryptographic assurance. Providers implement background processes to reassign blocks securely, often leveraging encryption and key revocation at scale. Tenants must rely on provider controls, contracts, and certifications to guarantee proper sanitization. This reliance underscores the importance of transparency. Customers need assurance that when they delete data, it is not only logically hidden but also protected against remnants in the shared infrastructure. Cloud abstraction changes the sanitization question from "how do I erase this disk?" to "how do I prove the provider enforces deletion policies effectively?" Object storage systems add complexity through versioning and delete markers. When versioning is enabled, deleting an object does not eliminate its prior states, but simply adds a marker that hides it from standard queries. These prior versions remain accessible until explicitly purged or until lifecycle rules expire them. This means that deletion policies must address not only current data but historical versions as well. Organizations relying on object storage must understand that delete may not mean erase, and must configure versioning and lifecycle rules to align with retention policies. Without coordinated action, sensitive data could persist indefinitely, concealed but not eliminated, creating hidden liabilities. Snapshots and replicas also create persistence layers that complicate deletion. A file or volume snapshot captures a point-in-time copy, and unless these are deleted, underlying data may survive even after the primary dataset is removed. Similarly, replicated datasets spread across zones or regions can continue to exist long after local deletion. Coordinating deletion across these secondary layers is vital to ensure true sanitization. Otherwise, organizations risk situations where sensitive data believed to be purged lingers in a forgotten snapshot or replica. The principle is clear. Every copy must be accounted for. Effective sanitization in cloud environments means expanding scope beyond the original dataset to include every dependent copy and derivative. Customer-managed keys provide tenants with a measure of control over crypto erase in cloud-hosted environments. By managing their own encryption keys, tenants can revoke or destroy them when data must be sanitized, without waiting for provider intervention. This approach empowers organizations to prove that deletion has occurred, since once the key is gone, the provider itself cannot decrypt the data. Customer-managed keys thus bridge trust gaps, placing some aspects of sanitization back in tenant hands. The trade-off is responsibility. Key management must be disciplined, and revocation must be deliberate, documented, and irreversible. Properly implemented, this model offers both control and assurance, aligning deletion with tenant-driven policy and compliance needs. Provider decommissioning processes represent the unseen backbone of secure deletion in the cloud. When hardware is repaired, recycled, or discarded, providers must sanitize drives before they leave the data center. This often involves cryptographic erasure, multiple overwrites, or physical destruction, depending on the classification of the data once held. Customers depend on these practices, but rarely see them directly, making certifications and audit reports essential. Providers that adhere to NIST SP 800-88 or equivalent standards give tenants confidence that residual data is not inadvertently exposed when hardware changes hands. These processes highlight the shared responsibility model. While tenants manage logical data deletion, providers guarantee physical media sanitization. Certificates of destruction provide tangible proof that sanitization has been carried out. Whether generated by a provider decommissioning drives or by an internal IT team wiping devices, certificates document the method used, the date, and the person responsible. For regulated industries, such certificates are not optional. They form part of the compliance evidence required during audits or legal proceedings. They also provide assurance to stakeholders that secure deletion is not merely claimed but demonstrated. Certificates of destruction are the paperwork that transforms sanitization from a technical task into an accountable business process, anchoring trust in formal documentation. Legal holds and retention policies complicate sanitization by superseding deletion requests until explicit release is granted. When litigation or investigation requires preservation, data cannot be deleted regardless of standard lifecycle rules. Attempting to sanitize prematurely may violate court orders or regulatory mandates. This interplay requires careful integration between retention governance and deletion workflows. Systems must recognize when holds are active and defer sanitization until lifted. The result is a hierarchy of obligations where legal preservation takes precedence over lifecycle minimization. Balancing these requirements ensures compliance with both security and legal duties, avoiding costly missteps that could undermine trust or invite sanctions. Multi-tenant isolation underscores the importance of strict process controls in cloud environments. Unlike on-premises systems where storage may be dedicated, cloud platforms intermix data from many tenants across shared infrastructure. Proper sanitization ensures that when one tenant deletes data, no remnant remains accessible to others. Providers must enforce strong separation through logical partitioning, cryptographic isolation, and rigorous workflows for data reassignment. Without such safeguards, remnants from one tenant could leak into another space, violating confidentiality. Multi-tenant isolation thus represents both a technical and contractual promise, reassuring customers that their data lifecycle ends cleanly without cross-contamination in shared environments. Verification strategies close the loop by confirming that sanitization actually succeeded. Logs provide event records, sampling validates data absence, checksums ensure overwritten blocks no longer match prior values, and attestation records certify compliance. Without verification, sanitization remains an assumption rather than a proven fact. Verification is especially vital in regulated industries, where failure to prove deletion may result in fines or reputational damage. It also reassures stakeholders internally, showing that policies are not only written but actively enforced and tested. Verification turns deletion from a hopeful act into a demonstrable guarantee, aligning technical execution with organizational accountability. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Lifecycle policies in object stores bring automation to secure deletion by governing when data expires, transitions to different storage classes, or is permanently purged. These policies act as rules engines. Administrators can define that files older than 5 years are automatically deleted or that objects with certain tags expire after a regulatory retention window. Without automation, deletion becomes a manual and error-prone task, leaving organizations vulnerable to forgotten data persisting indefinitely. Lifecycle policies not only improve consistency but also provide predictability for compliance. Much like a library with automated return deadlines, lifecycle rules ensure that data leaves the shelves when its borrowing period is over. Automation guarantees that sensitive data does not linger, while still allowing customization for nuanced business and legal needs. Databases pose unique challenges for deletion. because sensitive information can hide in multiple layers beyond the primary tables. A user record may be removed from the main table, yet residual traces remain in indexes, logs, caches, and temporary files. To achieve true sanitization, deletion workflows must encompass these secondary structures. Modern database systems often provide secure purge features, but administrators must validate that they extend beyond the surface. This is crucial in regulated industries where even fragments can constitute a compliance violation. The process is like erasing chalk from a board. Not only must the obvious writing disappear, but smudges in the corners must also be scrubbed away to ensure nothing legible remains. File storage deletion often extends beyond simply removing a primary file. Snapshots may continue to hold prior versions, recycle bins may retain deleted items for recovery, and shared links can provide lingering access to cached copies. Coordinated deletion must address all these layers, ensuring that when a file is truly retired, no hidden remnants remain. Otherwise, organizations risk believing they have sanitized information when, in reality, residual pathways persist. The complexity grows in collaborative platforms where sharing and versioning are core features. Effective sanitization requires deliberate workflows that close every door, not just the front entrance. True file deletion resembles dismantling a house. Not only must the doors be locked, but the spare keys must also be collected and destroyed. Block storage environments present another distinct set of sanitization requirements. Cloud providers often offer wipe-on-delete features, ensuring that when a block volume is deprovisioned, its contents are overwritten or cryptographically rendered unreadable. Secure detach operations may also revoke access keys, ensuring no stale mappings remain. Crypto arrays can further enforce guarantees by revoking keys tied to encrypted block volumes. These mechanisms must work together seamlessly, since block storage often holds high-value workloads like databases and virtual machine images. Without coordinated assurance, deleted block volumes could leave residual traces accessible to subsequent tenants. Treating block storage deletion as a multi-step process ensures completeness, with both logical and cryptographic safeguards in place. Backups and archives complicate deletion because they exist specifically to preserve data beyond the primary system. Deleting a record from a database does not automatically erase it from backup tapes, cloud archives, or replicated stores. Effective deletion requires alignment across purge jobs, retention schedules, and crypto arrays of associated encryption keys. Otherwise, sensitive information may persist long after intended deletion. Organizations must therefore integrate backup lifecycle governance with data sanitization policies, ensuring that the promise of deletion extends consistently across every copy. It is much like cleaning up hazardous materials. Not only must the surface be scrubbed, but every container, glove, and cloth used must also be disposed of securely to prevent recontamination. In multi-cloud environments, harmonizing deletion procedures is essential. Each provider may offer different capabilities. Some emphasize crypto erase, others focus on overwrite or lifecycle automation. If organizations fail to coordinate, inconsistent practices can leave data remnants scattered across platforms. Harmonization means defining a uniform baseline of sanitization, applying it consistently, and validating across all providers. It also requires understanding differences in terminology, logging, and evidence generation. Without this alignment, the weakest provider becomes the weak link in a chain of protection. Multi-cloud deletion is like maintaining safety standards across factories in different countries. Each must meet a common bar, or the entire supply chain risks contamination. Key rotation, while important, is not sufficient for true sanitization unless prior keys are unrecoverably destroyed. Simply generating new keys without securely retiring the old ones risks leaving doors open to past data. Attackers with access to an old key can still decrypt historical content unless the key is deliberately purged. Effective sanitization means closing these cryptographic windows completely, not just locking them temporarily. Organizations must therefore treat key destruction as a deliberate life cycle event, ensuring that once keys are rotated out, they can never be resurrected. Without this discipline, key rotation may provide only a veneer of security, leaving underlying data vulnerable to future compromise. Escrowed and backed-up keys must also be included in the scope of crypto erase. Many organizations maintain escrow services or key backups to ensure continuity, but if these copies are overlooked during sanitization, data may remain restorable even after primary keys are revoked. True crypto erase requires a sweep across every repository, escrow system, and backup vault where keys reside. This process demands thorough documentation and auditable records, proving that no shadow keys survive. It is akin to ensuring that every duplicate of a house key is retrieved, not just the one on the owner's keychain, but also the copies held by neighbors, relatives, or locksmiths. Comprehensive scope ensures the promise of irreversibility. Chain of custody records form the backbone of accountability in secure deletion. These records identify who authorized deletion, who executed it, when it occurred, and what evidence was generated. Such documentation transforms deletion from a technical task into an auditable event. In regulated industries, chain of custody provides the necessary assurance that sanitization was performed properly and without tampering. It also creates accountability within organizations, ensuring no single individual can erase sensitive data without oversight. These logs function much like legal records for property transfers, proving ownership and intent. In the world of data, chain of custody is the notarized stamp that validates deletion as both genuine and verifiable. Classification labels drive the rigor of sanitization, linking the value and sensitivity of data to the required assurance level. For public or low-sensitivity records, clearing may suffice. For regulated personal data, purging with crypto erase may be mandated. For national security or trade secrets, only physical destruction might be acceptable. Labels also determine evidence depth and approval workflows, ensuring that the effort expended on sanitization matches the stakes involved. This tiered approach aligns resources with risk, preventing both overkill and underprotection. It is comparable to airport security tiers. A local commuter flight does not require the same scrutiny as an international one, but both demand measures proportionate to their context. Processor and subprocessor contracts must codify sanitization responsibilities, especially in cloud and outsourcing arrangements. Customers need legal assurance that providers will sanitize data according to agreed standards and that they retain the right to verify. These contractual terms define accountability and recourse if sanitization obligations are not met. They also clarify who handles verification, evidence generation, and retention of destruction certificates. Without such clauses, customers may lack visibility or control over how their data is retired. Contractual commitments transform sanitization from a matter of trust into an enforceable obligation, embedding data protection into the very fabric of business relationships. Log governance presents a unique tension in secure deletion. On one hand, logs must preserve integrity for compliance and forensic purposes. On the other hand, they may inadvertently contain fragments of sensitive data queries, identifiers, or tokens that require redaction. Effective log governance ensures that sensitive values are masked or removed, while the logs themselves remain tamper-proof and auditable. The balance is delicate. Over-sanitizing logs risks breaking correlations, while under-sanitizing risks exposure. It is like editing a transcript for public release. Names may be redacted for privacy, but the sequence of events must remain intact. Thoughtful governance preserves both security and evidentiary value. Incident response playbooks increasingly include emergency crypto erase as a containment measure. If data stores or keys are compromised, immediate revocation of access can limit damage by rendering captured data unreadable. These playbooks define triggers, roles, and escalation paths for rapid response. They must be rehearsed to ensure that emergency sanitization is both swift and precise, avoiding accidental erasure of unaffected systems. Crypto erase as a defensive maneuver is akin to scuttling a ship to prevent its capture, a drastic but effective measure that prioritizes denial of access over preservation. Including such contingencies in incident response ensures readiness for worst-case breaches. Anti-patterns provide lessons in what not to do when attempting secure deletion. Ad hoc scripts without verification can leave remnants behind, unmanaged snapshots may preserve sensitive versions indefinitely, and orphaned backups can silently undermine sanitization efforts. These missteps highlight the danger of treating deletion as an afterthought rather than a structured process. They serve as cautionary tales. Organizations that ignore formal methods risk data resurfacing long after it was presumed destroyed. Anti-patterns reinforce the need for policy-driven, repeatable, and verifiable approaches rather than improvised shortcuts. As with any discipline, consistent methodology distinguishes true security from illusions of safety. For exam preparation, it is essential to recognize which sanitization methods apply in different scenarios. The exam may ask when to use clear, purge, or destroy, or when crypto erase is more effective than overwriting. Learners must also understand the importance of certificates, chain of custody, and verification artifacts in proving compliance. Cloud contexts require special focus, as logical deletion, snapshots, and multi-tenant isolation complicate sanitization. Mastery comes not from memorizing terms, but from appreciating how technical, legal, and operational factors converge. The ability to select methods that fit context demonstrates readiness for both the exam and real-world application. Secure deletion achieves its promise only when guided by policy, coordinated across systems, and proven with verification and evidence. Crypto erase delivers speed and scalability, while traditional sanitization offers physical assurance. Together, they prevent data from lingering in forgotten snapshots, orphaned backups, or residual media. With chain of custody, contractual commitments, and regulatory alignment, organizations can demonstrate not just intent but compliance. In conclusion, secure data deletion is not simply erasing bits. It is the assurance that sensitive information cannot be reconstructed once its life cycle ends. In cloud systems, this assurance protects privacy, preserves trust, and fulfills the duty of stewardship that organizations owe to those who entrust them with data. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.